Imagine you're tasked with creating a service robot for a busy hotel. Your goal is to design a machine that can independently navigate crowded hallways to deliver breakfast straight to a guest's door. To do that, the robot needs to be stable enough to roll over carpets without tipping and narrow enough to smoothly slip past people. But before you pick up a single tool, you have to translate those physical goals into a set of strict hardware rules. For this project, we've set specific targets: carry a 5-kilogram payload, travel 1 meter per second with 3 centimeters ground clearance so that it can handle uneven floors. These initial rules dictate the structural layer cake design of the robot, ensuring every engineering choice serves a specific purpose. To get the robot moving, we're using a differential drive system. It's one of the most reliable and cost-effective ways to help a robot navigate indoors. The mechanics are simple. 2 independent motorized wheels in the center handle the movement. By spinning the wheels at different speeds or in opposite directions, the robot can turn in place. 2 caster wheels at the front and back keep the frame balanced. To find the right motors, we compare our target speed against the circumference of our 9-centimeter wheels, calculating the exact RPM needed. Next, we have to account for torque. This pushing power overcomes friction to move our 15-kilogram robot from a dead stop. We calculate it by seeing how weight is distributed across all 4 wheels. Finding the downward pressure on the motorized wheels reveals the exact torque required. Solving these 2 equations removes the guesswork. We can now select the specific motors that are sized correctly for the job. Now that we have our measurements, we need to design the physical body. To do this, we create flat 2D blueprints that a factory can use to cut our materials. We use a drafting tool called LibreCAD. It allows us to organize our drawings into digital layers, which helps keep the complex measurements of the different plates separate and clear. This is the blueprint for our base plate. 2 rectangular sections are cut out of the edges, allowing our motorized wheels to pass through. We also include 4 small circles inside the plate as mounting points for the support poles. These 2D CAD files act as the precise map a manufacturing machine needs to cut the physical parts of the chassis. Even with perfect drawings, manufacturing physical parts is expensive. To make sure everything fits together correctly, we first perform a virtual test run in 3D. We'll use a 3D environment called Blender, but instead of modeling the robot by hand with a mouse, we're going to generate the entire thing using a Python script. By using Python code, we can instantly spawn a perfectly scaled cylinder for our base plate. If we need to change the size later, we just update 1 line of code. To create the wheel slots, the script uses what's called a Boolean difference modifier. You can think of this as a digital cookie cutter. The script places 2 cubes where the wheel should go. When the modifier is applied, the cubes disappear, carving those exact slots right out of the base plate cylinder. Building the model with a script ensures the geometry is consistent and easy to adjust without having to redraw the entire robot from scratch. The script then automatically stacks the middle and top plates onto the support tubes, completing the 3-layer structure. We also add placeholder shapes for other hardware, like the caster wheels and the navigation sensors, such as this Xbox Kinect. Once the model is assembled, we export the entire mesh into an STL file, a format that virtual testing programs can easily read. This allows us to watch the robot driving forward in a simulation. We can check the balance and wheel movement before we ever commit to building the real thing. This pipeline, from mathematical requirements to 2D drafting and 3D coding, lets us verify our logic and catch design errors in the virtual world. It makes the eventual transition to the physical factory floor much more predictable.